Okay, good morning and welcome back to our Teknik Digital Core. This is a recorded session because yesterday I haven't been able to deliver the material on real time. So as we agreed that we can use the recorded session. So today is our last class. Oh, okay, great. Okay, send it. Okay, sorry for the delay. Actually, we on the process on migrating from Google Cloud to Microsoft Azure. Okay, come on. Need to do all this. Okay, secure is secure, but it's a little bit annoying. Okay, today I believe is our last class. So after this, we're going to have the final exam. And for your information, the final exam will be delivered in online and also in multiple choice and also true and false. And then, okay. So today we're going to discuss about how to design a sequential machine, part 2. Because last week we already discussed about this, how to design this machine sequential machine. And today we're going to continue to discuss how to design a sequential machine. So last week we already part Okay, I got confused. This is the concept, and then we'll discuss about. Oh yeah. So we're going to start from not this one because we already discussed about this last week. So we're going to discuss about this one. Okay. Practice number 1. Okay. Just like last week, there are two parts of how to design the sequential machine. Is the first one is starting from the case study, a story. From story, you can create the state diagram, and then from the state diagram, you can create the FSM. And from last week and also part of this week, we're going to discuss about how to design the FSM starting from the state diagram. So we are given a state diagram. We are supposed to create and design the finished state machine. Now, we have the state diagram. It's a very simple, probably the simplest state diagram. In here, first we need to identify how many inputs. To identify how many inputs or how to determine the number of inputs in the FSM, we just need to check whether a state will move to another state depend on a variable. But in this case, in this state diagram, there is no variable in the changing from one state to another, which means the changing of states only depends on the clock. So for example, right now, the present state is 0, and then clock. Then it will move to 1. So the present state is now 1. Now clock again. Then it will move back to 0. Clock again, move to 1. Clock again, move to 0, etc. So there is no input in this state diagram because there is no variable that the changing will depend upon. So how many inputs? 0. Now, how many output? Yes, there is an output in here, X. So there is one output, which is X. And then how many flip-flop? To identify how many flip-flop, to identify how many flip-flop in the FSM, we just need to count how many variable state inside the state. In here, every state only has one variable state. That means we only need one flip-flop. Now, after this, we can start to create the FSM, starting with which flip-flop do we use? Is it data flip-flop, or is it toggle flip-flop, or is it GK flip-flop? Then create the logic to create output, and then create the logic to create the next state combinational logic. Okay, now let's start to create the FSM using this based on this state diagram. First, using the data flip-flop. From earlier discussion, we understand that this is the next state combinational logic, and then this is the data flip-flop, and then this is the clock, and this is the output Q. This is the output Q naught, and then this is the output combinational logic, and this is the output, which is in this case is X, and then there is no input in here. So the input only comes from the present state. So this is the block diagram of the our sequential machine. Now, what is inside this output combinational logic? Because there's the next step, this one. Create the logic inside the output combinational logic. Now, X as the output will active only when the present state is 0. So when Q, this is Q, when Q is 0, then the output is active. X is active. However, when Q is 1, then X is 0. So that means X is Q naught. So this is X, sorry. So this is for X. Okay, finish with the output combinational logic. Now we start with the next state combinational logic. One input, which is Q. So it will be either 0 or 1. And then the output will be D flip-flop. Now, how can we identify what is the value in here and what is the value in here? To enter this value in the K-map, we need the transition table. This is the transition table. The table that explains the output 0, clock, stay 0, will be happen when D is 0. For example, like that. Okay, now Q is 0. So that means we are here. The present state is 0. Now, clock, it will change to 1. So from 0, clock to 1. So this is the transition from 0 to 1. That will happen when D is 1. So D is supposed to be 1. And then D, now Q is 1. Clock, it will change to 0. So from 1 to 0. This is the transition from 1 to 0. This will happen when D is 0. So D is 0. So D is Q naught. So the circuit will be very simple. D comes from Q naught. So we're done. Okay. Now, how do we implement this state diagram, the same state diagram, but now it's using J, K flip-flop. Starting from the block diagram, this is for J, K, and this is for the clock. This is Q, this is Q naught, and then this one is X, just like from our last example. Now, suppose the feedback is start from the Q. So Q could be 0, it could be 1. This is for the J, and this is 0, 1 for K. Now, Q is 0. That means we are here. The present state is 0. Clock, it will change to 1. 0 to 1. This is the transition, 0 to 1. That means J is 1 and K is don't care. Okay, now Q is 1. When Q is 1 and then clock, it will change to 0. So the transition is from 1 to 0. This is transition, which means J is supposed to be the don't care and K is 1. So this means J is 1, K is also 1. So this means there is no feedback. But we're going to connect J and K with 1 or 5 volt. That's it. That's for JK flip-flop. This is for D flip-flop. This is for JK flip-flop. Now, how about for the T flip-flop? Same thing. This is for the clock. This is for the Q. This is for the Q naught, and this is X. And then we're supposed to have this one. And then this is Q, 0, 1, this one for T. When Q is 0, so we are here, clock, it will change to 1. 0 to 1 happen when T is 1. Now, Q is 1. 1 to 0. 1 to 0 happen when T is 1. So T is 1. So it's similar like the JK flip-flop. So the solution is something like this. Okay. Now, this is problem number 2. You can easily create the solution from here. How many inputs? Right now, we have a variable that will change the state from 0 to 1 or 1 to 0 or 1 to 1 or 0 to 1, which is, in this case, the input is A. The variable is A. So how many inputs? 1, which is A. How many output? 1, which is X. And how many flip-flop? 1, because there is only one variable state inside the state. Now, which flip-flop do we use? Do we use D, JK, or toggle flip-flop? They depend on our design. Now, let's start with the D. Just one example here. So we have A, and then we also have D. This one is Q, and this one is X. Now, X happen when Q is 0. So X is Q naught. Q naught. Okay. Now, we have two inputs, which is Q and A, 0, 1, 0, 1. This one is for D flip-flop. Now, Q is 1. So we are here. What happens when A is 0? When A is 0, 0 stays 0. 0 stays 0, which means D is 0. How about when A is 1? When A is 1, then it will change from 0 to 1, which means D is supposed to be 1. Yes, this one. Now, how about Q is 1? So we are here. A is 0. When A is 0, it will stays 1. 1 stays 1, which means D is 1. And then A is 1, then it will change from 1 to 0. From 1 to 0 happen when D is 0. So D is A Q naught plus A naught Q, or A short Q. So it's actually something like this. A short Q. Okay, well, you can just continue this one. How about with JK? Okay, this is A, and then this one is J, this one is K, and then this one is clock. This one is Q, this one is Q naught, and then this one is X. Let's try to change from here. So we have QA0101, and then this one is for J. QA0101, this one is for K. Now Q is 0, so we are here. A is 0, which means 0 stays 0. This will happen when J is 0 and K is don't care. What happens when A is 1? So it will change from 0 to 1. 0 to 1, which means J is 1 and K is don't care. Okay, now what happens when Q is 1? So we are here, and A is 0. A is 0, which means 1 stays 1. So J is don't care, and K is 0. And then the last one is 1, change to 0. So J is don't care, and then K is 1. So the group is J is A, and K is A. So there will be no feedback in here. However, we can just directly connect A to J and also A to K. That's it. This is the implementation of the FSM from this state diagram using JK flip-flop. Okay. Last one is using the toggle flip-flop. A, and then this one is for the toggle flip-flop, and then this one is for the clock. Q and Q naught, and this one is for X, and this one is supposed to be here, and then this one is Q A0101. This is not for T. Now Q is 0, so we are here. A is 0, which means 0 stays 0. T is 0. 0 change to 1 because A is 1. 0 to 1, which means toggle is 1. How about 1 to 0? 1 to 0 is here. 1 to 0 is 1. And then when A is 0, 1 stays 1. So this one stays 1. So T is A. So similar like T, JK flip-flop. So this is the solution. Okay, now the last one is how to design the diagram state, because previously we only discussed about how to create the sequential machine starting from a state diagram. But right now, how can we create the state diagram using a case study? So the case study number 1 is for the sequence detector. Sequence detector is a machine that can detect a sequence. Like for example, I want to check whether the input is 1, 1, 0, 0. If this data comes in parallel, it will be very easy to find this specific pattern. So we just create this combination logic with AND gate and 2 inverter, which will create the output of 1 only when the input is 1, 1, 0, 0. Only this combination will create the output 1. This is very easy. However, if the data comes in sequence or in series, now we have a problem. It needs to detect 1, and then 1, and then 0, and then 0. This will create several combinations. Let's say starting from 1. If the next input is 1, okay. So if the, okay, let's start from the beginning. Now, if the first input is 1, then it will move to this state. However, if the input is 0, it's supposed to stay here. Okay, okay. Let me refresh it again. Now, let's say the first combination is the input is 1, and then 1, and then 0, and then 0. Then this is the final state, which means the output is supposed to be active. Oh, I have detected 1, 1, 0, and 0. However, there will be lots of combination. How about if the first one is 0? How about the next one is 0? How about the third one is 1? How about the fourth one is 1? Where should we go from here? This is the problem. So you need to understand the situation and think in logics to create the state diagram. First, how many input do we need? Sure, we only need one input for the FSM because the data comes in series or in sequence. How many states do we need? Okay, so we need 5 states in this case. The first state is nothing is detected. Not the first one. Now, the second state is state where only one bit is detected. And then, remember about our previous example. First is 1, and then 1, and then 0, and then 0. So this is the state of nothing is detected. And this is the state where one bit is already detected. And this is the state where 2 bits already detected. And this one is 3 bits detected. And this one is the last one is the 4-bit already detected. So this is the final status, final state. All 4 bits are detected, which are 1, 1, 0, and 0. So we need 5 states. This is the first state. This is the second state, third state, fourth state, and 5, and the 5th state. Okay. Now, let's draw all the 5 states. Also, give the variable state. Because we have 5 states, we need 3 variable states. Because if we only use 2 variable states, that means we cannot identify. We can only identify 4 states. Sorry. So we need 3 variable states. Let's say starting from 0, 0, 0, and then 0, 0, 1, 0, 1, 1, 0, 1, 0, and 1, 1, 0. This is the state where nothing is detected. And this is the state where only 1 bit is detected. This is 1 bit. So this. And this is the state where only 2 bits are detected, which is bit 1 and then bit 1. And then this one is the state where only 3 bits are detected. So 0, 0, 1. And then this is the last one. All 4 bits are detected, which is 1, 1, 0, and then 0. Okay, now what happened when this one is 0, and this one is 0, this one is 1, this one is 1. Where should we go if that happened? Now, right now we have to think logically. What happened if the first input is 1? So we're going to change from that state 0, 0, 0 to 0, 0, 1. However, what happened if the first input is 0? If the first input is 0, then it will stay in the state where nothing is detected. Because if the first input is 0, then nothing is detected. Because we expect the first input to become 1. Okay. Now, what happens if the second input is 1? So we just change the state to 0, 1, 1. However, what happens if the second input is 0? If the second input is 0, then it will return to the state where nothing is detected. What? Why? That's because we expect 0, we expect 1 and then 1. But it happened that the sequence is 1 and then 0. If that happened, then we start from the beginning. Nothing is detected because we are expecting 1 and then 1. But it happened to become 1 and then 0. So nothing is detected. Okay. Now, what happens if the next input is 0? So it's pretty easy. Just change to the state to 0, 1, 0. However, what happens if the input is 1. What happens if the third input is 1? So it will become 1, 1, and then 1. It will stay here. Whoa, whoa, why? That's because if the input is 1, and then 1, and then 1, we are still in the state that 2 bits are detected. This is the state where 2 bits are detected, 1 and 1. So because 1, 1, 1, hey, it's still 2 bits of 1. So it will stay there. Next is, oops, sorry. Next is the last one. What happens if the third input is 0? Easy. It will change to the state 0, 1, 1, 0. How about if the next input is 1? So it will happen that 1, 1, and then 0. Almost there. It's supposed to be 0, but comes with 1. Oh my, it's 1. That means we start not from the beginning, but we already detect the first input. So it will move to the state where 1 bit is detected, which is 1. Okay. Is this the end? Yes, probably the end. So this is the state diagram. You can implement this state diagram using FSM. Or maybe we want to create the system or create the detector to detect, undetect, undetect, detect again and again. So that means it will not end in here. It will start the detection again from the beginning. So that means right now, what happens if the next input is 0 or 1? If the next input is 0, it will move to here because we are expecting the first input is 1, right? But it gives 0. Because it gives 0, then nothing is detected. So that's why it will change the state to the beginning, the state where nothing is detected. However, if the next input is 1, then we can assume that, okay, this is the first bit we detected. So we change to here. Okay, so this is the state diagram if we want the system to detect repeatedly. Okay, so this is the end. Let's check. Maybe last year's exam, probably from 2019. Do we have bias? Okay, this one. Now, this is the final exam from what 3 years ago, I believe. Yes. Now, we are aware that there is an integrated circuit that will behave to decode a BCD to 7 segment. So we call it a BCD to 7 segment decoder. So right now, you are asked to create the combination logic to decode the input of A and B to turn on the 7 segment accordingly. For example, if this one is A, this one is B, if A 0 and B 0, it will represent the value of 0. So the format represented by the 7 segment will be 0 like this. So it will turn on A, B, C, D, E, and F. If this one is 0 and 0. So it will show the number 0. How about if A 0 and B is 1? So it's supposed to turn on B and C, the lamp of B and C from the 7 segment. How about 1 and 0? It's supposed to show the value of 2. How about 1 and 1? It's supposed to show the value of 3. How do we do it? Well, it's similar like how we design the combination logic. This is the output and this is the input. So we have 7 output. So we're going to have 7 K-map. This one A, B, 0, 1, 0, 1, A, B, 0, 1, 0, 1, A, B, 0, 1, 0, 1, then etc. And then the last one. This one for the lamp A, this one B, C, D, E, F, and the last one is for C. Now, when A is 0 and B is 0, the output of the combination logic is supposed to turn on A, B, C, D, E, F. So when A is 0, B is 0, it's supposed to turn on A, B, C, D, E, F, but no G. Okay, now how about 0 and 1? 0 and 1 is supposed to turn on B and C. B and C, so the rest are 0. Now, how about A is 1, B is 0, A is 1, B is 0, so it will turn on A, B, but not C, and then D, and then E, but not F, and also G. Okay, hope you still remember that this is A, B, C, D, E, F, G. Okay, now the last one is 1 and 1. 1 and 1 is supposed to turn on the lamp of A, B, C, D, and G. A, B, C, D, and G. Okay, so A is A is A plus B naught, and then B is 1, C is A naught plus B, okay, and then D is B naught A plus B naught, same like A, and then E is B naught, and F is A naught B naught, and then G is A. Then based on this function, you can just create a circuit. For example, this is A, this is B, and then this is, let's say this one is A. A is A plus B naught. A plus B naught. And then what about B? B is 1. So B is 1. How about C? C is A naught plus B. A naught plus B, etc. You can get to D, E, F, and G. Okay, this is the solution. And then based on the state diagram, create the FSM. We already done this one. This is the sample as we discussed earlier. And then, okay, based on the state diagram in number 2, this one, complete the timing diagram below when D flip-flop active on the rising edge. So it will active or it will read the input on this rising edge. Okay. Now, X is here. X is 1, which means it will represent the present state. So, because X is 1, right now we are here. Now, clock. On the first clock, A is 0. Now, because A is 0, then it will remain 1. Oh, sorry, my mistake. X is 0. Because X is 0, then, sorry, my mistake. Because X is 0, so we are here. Now, clock A is 0. Because A is 0, it will stay 0. So the output of present state stays 0 until the next clock. The next clock A is 1. Because A is 1, then it will change to here. So it will change to 1 until the next clock. On the next clock, A is 0. Because A is 0, we are here. Because A is 0, then 1 stays 1. Now A is 1. Because A is 1, then it will change back to 0, 1 to 0. And then the next clock, A is 1. Because A is 1, it will change back to 1. And then the next clock, A is 0. Because A is 0, then it will stay 1. That's it. This is our timing diagram based on the state diagram. Okay. Okay, I think that's it for this recording. Remember, next week we're going to have the final exam, and you're supposed to have the final exam in multiple choice and also perhaps true and false. So many questions, but in detail, I'm going to inform you on the WhatsApp group. Okay, thank you and goodbye. And because this is the last class, I hope you are healthy and stay safe and stay healthy. Thank you and bye-bye.